Hello everyone. So in this video we are going to discuss about the properties of continuous time Fourier series. So we'll discuss various important properties of Fourier series, and we will use some convention. So I'll just show you one convention which I'll use throughout this lecture. So we will represent xt as our periodic signal with period t. So xt will denote the periodic signal having a period of t, and we'll represent ak as the Fourier series coefficient corresponding to this signal, and this arrow denotes the Fourier series representation. So xt has a Fourier series representation with ak as the Fourier series coefficients. So this convention will make the representation easy as we discuss different properties. So we'll start with the first property. The first property is the linearity. So let's discuss the property of linearity. So suppose we have two periodic signals xt and yt, and they are periodic and their period is denoted by t, and xt has a Fourier series coefficient as ak and yt is having a Fourier series coefficient represented by bk. So the linear combination of the two signal will also have the same period t, and that is quite significant. So suppose zt represents the linear combination of these two signal, and that is represented by a of xt so and b of yt. So we have multiplied two scalars to these signal and then we are added. So the corresponding Fourier series coefficient ck, which is corresponding to the signal zt, will be equal to a of small ak plus multiplied with capital B, that is the scalar, multiplied with the Fourier series coefficient of yt, that is bk. So as you can see, because of the linearity property, we will get the Fourier series coefficient of zt as a of ak plus b of bk. So we can directly write the Fourier series coefficient if there are some linear combination at the input. Now, so next we will discuss the time shifting property. So the second property we will discuss about the time shifting. So when time shift is applied to a periodic signal, the period t is preserved. So the time shifting operation does not affect the period. So suppose some signal xt has a period of t, and if we shift the signal by some amount, suppose t naught, then also the period of that signal will be t, and that is quite obvious. So the Fourier series coefficient bk of the resulting signal xt minus t naught may be expressed as, so we will represent the Fourier series coefficient of our bk, that is the Fourier series coefficient of the shifted version of that signal, as 1 over t from the definition integral over the period t x of t minus t naught e raised to the power minus j k omega naught dt. Now we will replace tau for t minus t naught. So what we will get? We will get 1 over t integral over t x of tau e raised to the power minus j k omega naught tau plus tau naught, sorry, this will be t naught, d tau, and that will be equal to e raised to the power minus j k omega naught t naught multiplied by 1 over t integration over the period t x of tau e raised to the power minus j k omega naught tau d tau. So, as you can see that this is the representation of our a k, that is the Fourier series coefficient of the signal x t, and we have some extra components e raised to the power minus j k omega naught t naught multiplied with a k for our Fourier series representation for b k. So, what it summarized to, suppose x t has a Fourier series coefficient of a k, then x of t minus t naught will have a Fourier series coefficient of e raised to the power minus j k omega naught t naught a k. So, this is the property of time shifting. Here is one interesting property to note, that when a periodic signal is shifted in time, the magnitude of its Fourier series coefficient remain unchanged. So, the mod of b k will be equal to mod of a k. So, the magnitude will not change and it is preserved. Next, we will discuss the property of time reversal. So, the third property which we are going to discuss is time reversal. So, the property says that if x t has a Fourier series coefficient of a k, then x of minus t has a Fourier series coefficient of a of minus k. And we can easily prove it also, like suppose y t is denoted by x of minus t. So, x of minus t, using the definition of Fourier series, we can write it as k from minus infinity to infinity a k e raised to the power of minus j k omega naught t, and now we will replace k with some suppose minus m, then what we will get? We will get the Fourier series representation of x of minus t, which is equals to summation m is equals to minus infinity to infinity a raised to the power a of minus m e raised to the power j m 2 pi t over t. So, this implies that b k will be a of minus k, and that we have seen that. So, this is the property of time reversal. Next, we will discuss the property of, so here is one interesting property arises, that if x t is even, so if x t is an even function, this implies that x of minus t will be equal to x of t, then the Fourier series will also be even. So, Fourier series will also be even, and if x t is odd, this implies x of minus t is equal to minus of x of t, then this implies that your Fourier series coefficient will also be odd, f s will also be odd. This implies that we will have a of minus k is equals to minus of a of k, and for this case we will have a of k is equals to a of minus k. So, this is an interesting property which arises from that time reversal operation, and you can easily verify them also by using the definitions. Next, we will discuss the property of time scaling. So, time scaling is a property which alters the period of the signal. So, it is a property which alters the period of the signal. So, suppose x t has a period of t, then x of alpha t will have a period of t over alpha. So, the time scaling property applies directly to each of the harmonic component of x t, and that implies that Fourier series for each of these component remain the same. So, suppose we will try to have the notion of x of alpha t Fourier series representation. So, we can write it as k is equals to minus infinity to infinity a k e raised to the power j k alpha omega naught t. So, as you can see that the Fourier series coefficients will not change. So, the coefficients remains the same, though the representation will change just because of the change in harmonics, but the coefficients will remain unchanged. So, this is the property of time scaling. Next, we will discuss the property of multiplication. So, we will discuss about multiplication. So, the property says that suppose we have x t and y t, which is both periodic with period t. So, x t has a Fourier series representation as a k and y t has coefficient represented by b k. Then suppose we multiply x t y t, we will get coefficient h k as summation L is equals to minus infinity to infinity a of L b k minus L. And if you will see this in generalized manner, this is the discrete time convolution. So, if you multiply the signal in your time domain, the Fourier series coefficient will be having a representation of discrete time convolution. So, this is the property of the multiplication. Next, we will discuss about conjugation and conjugate symmetry. So, let us discuss conjugation and conjugate symmetry. So, what it says that if suppose x t has a Fourier series coefficient represented by a k, and again x t is periodic signal with period t, then x star, that is the conjugate of x t, has a Fourier series representation of a star of minus k. So, how we can derive it? We can have a small derivation, though that is very easy. You can also do that. Suppose x t is represented with k is equals to minus infinity to infinity a k e raised to the power j k omega naught t. So, the complex conjugate of x t will be having a representation of a k star, and this will be e raised to power minus j k omega naught t. Now, we will replace k with minus k. What we will get? We will get x star t, which will be equal to k varying from minus infinity to infinity a of minus k star e raised to the power j k omega naught t, and if we will compare these two representation, you will get to this conclusion. So, this is the property of conjugation and conjugate symmetry, and there are some interesting points arise from it, that for a real signal, so for a real signal, we know that x t will be equal to x star of t, and it further signifies that a of minus k will be equal to a k star. So, this is a property for real signal, and we can try to merge two of the conditions also. Suppose if x t is real and even. So, if x t is real and even, then its Fourier series coefficients are also real and even. You can directly have the notion, because we already discussed the conjugate symmetry operation and time reversal operation. So, from there you can just get the idea of if x t is real and even, the Fourier series will also be real and even, and if x t is real and odd, the Fourier series will be purely imaginary and odd. So, next we will discuss the Parseval's relation. So, we will discuss the Parseval's relation. So, suppose we have a signal x t which is periodic and has a period of t. So, if we integrate 1 over t integration over a period mod of x t square dt, then it will be equal to summation k is equals to minus infinity to infinity mod a k square. So, this is the property of the Parseval's relation, and as we know that this quantity represents the average power. So, this can be shown for, suppose we discussed about the kth harmonics. So, for kth harmonics what we can write? We can write 1 over t over t. We will replace ak with its xt with its Fourier series representation. So, we can write it as ak e raised to the power j k omega naught t mod of this square dt, and that will be equal to 1 over t ak mod ak square dt, and that will be equal to mod ak square. So, for kth harmonics we got that the average power is equivalent to the square of the coefficients, and the total average power in a periodic signal then equals to the sum of the average power in all of its harmonics. So, that is the Parseval relation. What it states that the total average power in a periodic signal equals the sum of the average power in all harmonics. And we have shown by a small derivation that for kth harmonics the power is equals to mod of ak square, and similarly if we sum all the average power in all of its harmonic, we will get the total average power of a periodic signal. That is the relation of Parseval's. So, this is all about the properties of Fourier series. Thank you.